Okay, this will be an example of a sample proportions problem from section 7.2. It's actually a problem that we kind of did earlier in the year with just using simulations before we really knew all this stuff. And it's one about the overbooking airlines. So the situation, Air America is considering a new policy of booking as many as 400 persons on an airplane that can seat only 350. Past studies have revealed that only 85% of the booked passengers show up. Okay, so that kind of sounds like a population proportion, P. Estimate the probability that if Air America books 400 persons, not enough seats will be available. Okay, so we're kind of saying, what are the chances that the sample proportion, um, is 350 out of 400. So 350 out of 400, if you do the division there, that's going to give you a 0.875. Okay, so basically, um, from past experiences, again, 85% of booked passengers show up. They want to say, how likely is it that if you take 400 people, you're going to get a sample that has 87.5%. Okay, because if that happens, this thing's overbooked and not enough seats would be available. So let's see how we can tackle this. Can we use the normal approximation? So we have a couple conditions to check first. Okay, so to check some conditions, and you really do need to show this step. You can't just assume anything. Um, we want to make sure that the big one, the first one does this thing even follow a normal distribution? Okay, so to do that, if you remember, we had a couple things. To be normal meant the same conditions as a binomial. The n times p had to be bigger than or equal to 10. Okay, that's going to ensure we get that nice normal shape. And then n times 1 minus p also needs to be greater than or equal to 10. Okay, so I know we talked about that in class the other day. Now make sure you actually show your numbers being plugged in here. Okay, in our case, we have 400 persons. That's our n, and then our p again was given at the beginning. So we need to actually show that 400 times 0.85, is that greater than or equal to 10? And is 400 times 1 minus p, so that would be 0.15, is that also greater than or equal to 10? And you're going to want to do the calculations here. I didn't work out the numbers, but I know those both are. But again, get in the habit of actually showing what those numbers are. Okay, but these both work, so they're both good enough. So we got a normal approximation. Okay, so we know it's normal. We know bell-shaped curve. Now, do we know the mean, standard deviation, anything like that? Okay, so we know it's normal. Okay, and again, we do know the mean. From past experience, they said it's 0.85, 85%. Okay, let's see, can we get a standard deviation? Okay, and there is a formula for that, but that one also has a condition. Okay, is the population 10 times, or is it at least 10 times, I should say? Nope. Is the population at least 10 times bigger than the sample? Okay, because if it's not, remember this is the problem, if you're taking from a small population, um, they're not really independent and it just changes a lot of things. In this case, again, we're going to assume there are tons of flights and passengers, and if we take 400 of them, I'm assuming there are more than 4,000 total passengers. There's more than 10 times, so there's a very, very large population, so that's not going to be an issue in this problem. Okay, so what we're going to do, we have the formula for that standard deviation of the p-hats of the sample proportions, which is the thing we're making here. We know the formula is p times 1 minus p all over n, and it's a square root of that whole thing. Okay, so we're going to just throw that into a calculator. Again, we know p is 0.85, we know n is 400. So if we calculate that, so I'm going to go square root, there's p times 1 minus p. I would kind of do that in your head usually just to avoid too many things in the calculator. And that needs to get divided by n. Okay, and notice this whole thing is in the parentheses because we're taking the square root of the whole thing, including the divided by 400. So that's going to give us our standard deviation, point 0, I'm going to round it to 0.018, just as we write it down, 0.018. Okay, so that would be, if we went out, we can usually go 2 or 3 standard deviations out, so this number would be 0.85 plus 0.018, so whatever that would be, like 0.868, I believe it would be, something like that. So yeah, we can put that on there just to kind of see where we're at. And then of course we would be adding another standard deviation and another standard deviation. Okay, so our question, okay, going back to the top, how likely is it that we're going to get more than 350 people show up? Okay, so 350 out of the 400, that's going to be a problem. That's overbooked. Okay, and again, that as a decimal is 0.875. So if the proportion in our sample is that or higher, or if it's higher than that, I should say, we're overbooked. Okay, so 0.875, let's show where that is on our curve here. 0.875, it's going to be somewhere out, let's see, would it be past this one? It doesn't really matter, but if we added another 0.018, it'd be pretty close. So it's going to be somewhere around there. Okay, so it's not exactly at the standard deviation line, but our drawing doesn't have to be perfect. And what we want to do is figure out what's the probability of that. The yellow shaded portion, again, if the whole curve has 100%, what percent is in the yellow shaded region? Okay, so our process is, we know it's a normal situation here. Okay, we checked the conditions on that. Okay, we are shading our lower and upper bound. Our lower bound is 0.875, that's where we're starting. We want to go up, so big number. We know our mean, and we used a formula to get our standard deviation. Okay, so let's calculate that, and we will get an answer and make a conclusion, and this problem will be done. So I'm going to go into a normal CDF, second distribution. We're going from 0.875 all the way up to a big upper bound. We knew the mean was 0.85. The standard deviation is that 0.0178 that's in the previous answer, so I'm going to do this so it doesn't round it. If it's not in your calculator, just go ahead and type it in there. It won't change too much. But that's going to be our answer. Okay, 0.08, so about 8%. Okay, so about 8%. So that's going to be the area in here, about 8% chance that this thing gets overbooked. So the airline would have to decide, is it worth it? 8% of the time in the long run, they're going to be overbooked. Okay, so they're making a lot of money. Think if you're selling 400 tickets, 350 people show up. So I mean, if 8% of the time you're overbooked, 92% of the time, things work fine. So the company would have to decide, is this worth it or not? Okay, and one last thing, you might be asking, couldn't we have done this problem from the very beginning as a binomial problem? And you could, you actually can, and get an exact answer. The issue is probably before the calculators were so useful in computers, doing a whole bunch of binomial calculations, adding them all up manually was really difficult, and using this normal approximation is a lot simpler and a lot quicker. So it's a very similar problem that we could have done back in chapter 6, but this is kind of a little more common way to do it, I would say, using a normal approximation. Okay.